I just realized I've been talking this whole time and my mic was muted. Yeah. I'm sorry. Hi again. Awkward. How's it going, Emery? How's it going, Anna? Who else is there? Part 2, vaccines. Are you ready? Yeah, I'm gonna have to start over. I even forgot what I was saying. Oh yeah, I was saying, let me know if the music is too loud. I kind of tested it. Seemed okay. Never know. But while we're waiting for people to join, we'll wait like 5 minutes, around then. Let me know. Don't let me know. First, go to my Instagram page if you didn't see the quotes that I posted a few days ago, because you got time now. And when you come back, let me know what were some of your vaccine assumptions before this whole pandemic started. I guess there'll be some interesting answers. Yeah. I know one of the main ones was the fact that vaccines cause autism, which is one of the main things that anti-vaxxers use, I guess. But it was a bit stupid, that one, because it was based on one paper that was literally retracted. Yeah. Anyways, do you have any? Groove into the music. Why are you speaking like Yoda, Anna? Fine, I am. Yeah, just chilling. Yeah, we'll wait a few more minutes. Some people might join. I have no idea. If it's your first time here, how about you put a wave emoji in the comments? I want to see how many new people we have. This could be fun. With some green tea. Sounds good. TEA, by the way, Emery. TEA. What? Am I too low? Wait. Oh, can't go higher. I think my chair's a bit broken. Do this though. There we go. Yay, TEA, you got it. Heavy metals. Yes. Yeah, that's one of the things a lot of people try to mention is the heavy metals in vaccines, which are usually adjuvants, which basically help the vaccines be a bit more immunogenic, that basically help the vaccine do its job better. They're not there to harm you or anything. But it is interesting. Okay, so we've got a bit of science and a bit of Dutch on this side. I don't know how you would pronounce that. Te? Tea? I don't know. I'll just sit here awkwardly. By the way, I changed the time of the live stream because at 4 o'clock a lot of people are still at work and stuff. You need to let me know. Is this time more convenient for you guys? Is it better? Would you prefer earlier? Later? I'm open. I'm free. Let's do this. Yeah. Exactly, Anna. Misconceptions. Assumptions. Oh yeah, I can speak Dutch now. Anyways, I guess we're gonna start. It's already 8:07. Maybe people are still having dinner. I'll wait till 8:10 and then I'll start because we've got some fun stuff to talk about today. I guess we'll have a lot of questions at the end, mainly. Have you noticed I'm not hitting my mic? I got a new mic. That was a gargling sound, if I ever heard one. Did you have any vaccine assumptions, Imri? Just wondering, just wondering. It's interesting to know what other people think. Yeah, my lips are cracking up. Yeah. Don't knock your mic. Don't knock your mic. I should make t-shirts. Don't knock the mic. Don't knock the mic. Yeah, assumptions like vaccines are bad for you, or vaccines don't protect you, or the flu vaccine is useless. Stuff like that. What did you assume about vaccines without actually having any factual basis? Yeah. You're a good boy then. You're a good boy. Okay, guys. I think it's time to go. I think it's time to start. So, last week, I guess I don't have to introduce myself, or maybe I should. Hey everyone, welcome to Science Me Softly. My name is Elena and I am a scientist, and I love to talk about science with people like you. 2 weeks ago, we talked about the history of vaccines, and today we're talking about current vaccine technology. Gosh darn. Let's start again. We're gonna do a quick recap of last week, or 2 weeks ago. Anyways, we talked about smallpox and how it was causing a bunch of epidemics back in the day. It caused the fall of the Aztec Empire, and even Egyptian mummies were found with scars resembling smallpox. To kind of counteract the disease or prevent the disease, people started sniffing smallpox scab dust. Not very pleasant, but in fact, it was kind of effective. It was 10 times less fatal than actually catching smallpox naturally. And people who underwent this treatment did go on to have immunity to smallpox. If you fast forward a few years later, a certain Dr. Jenner in England is giving this 8-year-old boy some cowpox to prove that catching cowpox can indeed give you immunity to smallpox. True story or not? Not sure, but the boy did survive and he didn't get infected with smallpox in the end. Fast forward a few more years later, where smallpox is declared the first human disease to be eradicated. Quick summary. But of course, if you didn't see the episode and you want some more detail, the episode is linked in the description bar below. Just go check it out. And if you have questions, come back and we can discuss it. So why did I start with the history of vaccines? Well, the thing is that I started with the history of vaccines because without vaccines, we wouldn't be where we are today. You see, we're living longer and longer, and less of us are dying from infectious diseases. We're dying more from stuff like cancer and diabetes, degenerative stuff. And truth is, we wouldn't be here without vaccines, without this drop in infectious diseases, without this drop in childhood mortality. We wouldn't be here. So what exactly are vaccines and how do they protect us? Well, vaccines are prophylactics, meaning that they prevent disease. And they do this by stimulating our bodies to produce antibodies. And basically what vaccines are, they can be a live or a dead virus, but what viruses have on their surface? What viruses have on their surface are antigens, kind of these little things sticking out. And these antigens act like their ID card. So vaccines contain these antigens, and what they basically do is teach our body to recognize a pathogen without exposing ourselves to the whole dangerous pathogen. And up until now, that was done through a few ways, and I've mentioned a few. One was by giving you a dead virus. So the virus is dead, but its envelope is still there. The antigens are still there. The components that can induce an immune response are still there. An example of this vaccine is the flu vaccine. You can also be given a weakened virus, which is where you're given a live virus that has been weakened or attenuated chemically or using heat, meaning the virus is still alive, but it's a bit under the weather, like when you have a bit of flu or when it's a bit too hot outside. Yeah, it's not so active. Still immunogenic, more immunogenic than a dead virus, but not as immunogenic or as deadly as a live virus. And then the last type of vaccine is giving the subunit of the virus. So this is when you only give a part of the virus, and this part of the virus is the immunogenic part, the part that would induce an immune response in your body. An example of this is the Hep B virus, the hepatitis B vaccine. So what vaccines basically are giving yourself a little bit of a bad thing, and that's how vaccines protect us. They teach our bodies, they teach our immune systems to recognize a threat without exposing ourselves to the whole deadly thing or the really, really, really bad thing. But the thing is that traditional vaccines take way too long to produce. And you need a sample of the virus that relies on biological systems to be grown. So to produce a vaccine, you need the live virus that needs to be grown. It needs to be grown either to then be killed or then to be weakened. And sometimes you can weaken it through growing it, but this can take months and years. This can take weeks or months. And it's just not suitable to these new emerging diseases that are occurring. I mean, if we think back to some recent epidemics that we've had. We're talking about Zika or Ebola or even swine flu. We weren't able to produce any substantial treatments until after or soon after the threat had passed. It took a really long time. Another reason why we might want some newer technologies is because these old technologies aren't suitable for everyone. And I'm talking mainly about people who are immunosuppressed. You can't just give them a weakened or a dead virus and expect them to not have a huge immune response to it. Well, expect them to survive it. That's what I mean, to survive it. And third reason why you would want newer technologies is, as I mentioned before, is this rise in epidemics. And we had in the SARS in 2003, the first Zika outbreak occurred in 2007, and then there was the more recent one in Brazil. A less known outbreak that is currently occurring in the Middle East is the MERS one. We had Ebola not too long ago, and right now we are dealing with COVID-19. And the funny thing is that quite a few of these are caused by coronaviruses. And we need to be able to respond rapidly to these unknown future pandemics. And with our current technologies, that's simply not possible. New technologies need to be able to be developed rapidly. So there's a new disease emerging, or we hear about a new disease that's just starting up. We need to be able to develop new treatments quickly to be able to stop the transmission dead in its tracks. And in order to do that, we need to be able to have a large-scale production. So from developing the actual technology or the actual treatment therapy to actually producing it, we need to be able to produce a lot of it quite quickly. It also needs to be heat stable. So if we think back to the fact that some of the older vaccines rely on live viruses or pieces of the virus, most often these vaccines need to be kept at very cool temperatures, which just makes them unsuitable for certain countries and does therefore reduce their global availability. So newer technologies need to be heat stable and be able to be globally available. By hitting all these targets, we'll be able to be more responsive to emerging diseases. And the fact is that we managed to do that. And we've managed to reduce the time to produce a vaccine simply by using the body's own protein production mechanism. Let me explain. We're always producing proteins. Our body is constantly producing proteins. And we store that information, the instructions to produce proteins, in our DNA. And when our bodies need to produce a protein, the instructions to produce that protein are then encoded in what we call messenger RNA or mRNA, which is like a single strand of DNA. And this mRNA contains the instructions to produce a protein. This mRNA is read by a ribosome and the protein is produced. And this is how we produce proteins in our body. And what we've managed to do is hijack the system to produce new therapeutics. They're called non-viral vaccines, and they're basically based on DNA and RNA, so nucleic acids. And if you want a little bit more information about DNA and all that kind of stuff, we did a cool episode back on Instagram back in the day about CRISPR-Cas9, and I've linked that down below as well. Check it out. It was a cool one. But coming back to these non-viral vaccines that are based on DNA, they're based on nucleic acids, and nucleic acids are basically the genetic code. It's what makes up DNA. It's what the alphabet is to the English language, if you get what I mean. And by using nucleic acids, we're able to select the antigen or antigens that will induce an immune response. We can design the vaccines to induce the immune response the way we want to. And the thing is that back in the 90s, we could already synthesize mRNA in the lab. And we already knew that taking mRNA from, let's say, a rabbit and injecting it into cells from maybe a frog will cause the cells from the frog to produce the protein, the rabbit protein, and not the frog's protein. So we could already transfer mRNA between species. The problem was that mRNA is very quickly degraded by our natural degradation systems. But fear not, since the 90s, we've been able to find many ways to stabilize mRNA in the blood in order to develop therapeutics with it. So these days we've been hearing a lot about mRNA vaccines, and it may seem like they're coming out of the blue, but the truth is they've been 30 years in the making. What are mRNA vaccines then? Well, they're basically made of synthetic mRNA that codes for a part of the virus. So they're kind of like subunit vaccines, but they're different because they use your body's own protein production system to produce the antibody against which your body then produces, to produce the antigen, against which your body then produces the antibody, which is amazing. So basically, your body is producing the antigen that is then going to produce an antibody against, and then this antibody stays around. So if you ever get infected with the actual pathogen in the future, your body will recognize it straight away and be able to deal with it quite easily. So in essence, that antigen kind of instead of acting like an ID card, it becomes a wanted poster for this virus for this virus, and your body is able to seek it out and eliminate it. What we've done is we've digitalized vaccines, and you heard me mention before that we can design and pick the antigen that we want to induce immune response. And this is simply because we no longer need a sample of the virus to produce vaccines. All you need is a digital file. Yeah, scientists just need to download a digital file and then they can go on to make vaccines. What does this digital file contain? The genetic code of the virus. It contains its whole genetic code. And what you can then basically do is go in there and pick the parts that you know will cause an immune response. And then you can produce synthetic mRNA of those parts, which are then transformed in the vaccine. This basically means that from downloading that file to starting to produce a vaccine, this can happen in a matter of days. And then testing that vaccine, that could just be weeks. And that's exactly what we saw happen a year ago, and why so many people were shocked. But the thing is that there are advantages to this new system, to using mRNA as a therapeutic. It's not infectious. If we think back to older vaccine technologies, the weakened, the dead virus, the weakened virus can basically become activated again and then cause a full-blown infection. You don't want that. mRNA vaccines are also non-integrating, meaning they do not integrate into your genome. They do not enter into your DNA, do not change your DNA, right? They just contain the instructions to make the part of the virus that will cause an immune response. Best part is, mRNA doesn't just hang around. Even though we found ways to make it more stable in the blood, it's still degraded through normal cellular processes, so it doesn't accumulate. And even better, you can quickly scale it up and adapt it quickly. Remember how I said it was just an electronic file? Well, you can just basically have a different electronic file, start choosing different antigens, and using the same platform you used to produce the other vaccine, you can start producing a new one against a different disease. It's really quick. If you want to know a bit more about how sequencing has helped us produce vaccines, safer vaccines, more quickly, I wrote an article a few months ago. Again, down below, check it out. I know, self-promotion, but yeah, I need to, from time to time. That was not the mic, that was the desk. Anyways, so let's recap. What have we learned so far? What have we learned today? Well, vaccines protect us against infectious diseases that are caused by viruses. They do this by vaccines are basically a little bit of a bad thing that protect us against even worse things. And we need newer technologies because at the moment there's a rise in global epidemics. We're talking about SARS, we're talking about those 3 coronaviruses, the SARS, the MERS, and the COVID. Now, well, COVID is SARS-CoV-2, so it's the second SARS. There's a rise in epidemics, and we need to be able to respond really quickly in order to prevent the to prevent the rise in the number of pandemics that are occurring, to keep them contained. And traditional vaccines are just not suitable to respond rapidly to these emerging diseases. Fortunately, non-viral vaccines, such as those based on mRNA, allow us to respond a lot quicker and get vaccines to more people quicker, and thus reduce the harm done by these emerging diseases. And once again, mRNA therapeutics are not a new concept. They've been 30 years in the making, and we're just getting to really use them. But yeah, there we are. I'm done. If you have any questions, let's go. My mic is still on, isn't it? I really enjoy doing this episode because it's really relevant to what's occurring right now, and it forced me to dig into some really interesting stuff. A lot of things that I didn't really know about, actually. Whoops. Looks like there was a little problem. I think. Not good. So let me answer some of these questions here. I think Imri had a question. Whoop, whoop, whoop. Where's... Okay, so he said, okay, so he's heard a lot about when the corona vaccine was announced, saying how vaccines have GPSs in them. Yeah, I've heard about the chip in the vaccine. That's just hilarious. What if it did actually happen one day, though? Yeah, that's a... no trial for the COVID-19. Yep, they did do trials. They did do trials, and they're still doing trials, but yeah, they did do quite a few trials, because I'm specifically thinking about the AstraZeneca and the Pfizer vaccines. Those ones are based on the mRNA technology that I just talked about, and they started production very quickly, and everyone was quite shocked when they announced that they were starting clinical trials. But they based these vaccines on research that was done on the previous outbreaks, such as the first coronavirus outbreak, the SARS one, and the MERS one. Like, research is always ongoing, so if you think about how these mRNA vaccines work, it's not very difficult to then transpose anything that you've learned from one virus onto another and then go on to produce a vaccine. I'm glad everything sounds less scary than before, Anna. It does to me too. And so many people have been talking a lot about these vaccines and a lot of bad things, but the facts are here, the science is there, so. Anyways. Maybe 8 o'clock isn't a great time for people. Need to rethink that. Well, if there are no new questions, Anna, we can... Are who having vaccine? You're missing something in there. In there. Ooh. Well, send me the article. Maybe we can discuss this on Instagram. I wouldn't know if natural is better than vaccine acquired. Maybe it is. You can't. Oh, am I having the vaccine? Well, I actually had my second dose today. So yeah, I'm vaccinated. Yay. Will you guys get vaccinated if you're given the opportunity? Yeah, I'm looking down because my computer is down here and I have the chat, so I can read what you guys are sending me. Yeah, I'm not avoiding. Yeah. I think at some point we're all gonna have to make that choice. Well, everyone's gonna have to make that choice. I've heard a lot of talk about the vaccine passport. So I don't know how that's gonna play out exactly. Anna, I'm glad to help. Anyways, guys, it was awesome talking to you. Maybe we can move the chat over to Instagram. Could get interesting. But thanks for joining. Next month is actually a special month for me, for several reasons. But next month I really want to talk about a topic that's kind of dear to me, let's say. I want to talk about invisible diseases. And these are diseases that you might see someone who looks healthy and happy and alive, but they might be suffering on the inside and you do not know what it is. And there are several types of diseases that come to mind that I want to discuss. I think it will be in a slightly different format, maybe not a live, maybe more videos and interviews throughout the month of April. But follow me on Instagram to keep up to date with what's happening. And yeah. I'm really excited and looking forward to it because, it's going to be super interesting, especially, for you guys and for me too, to be able to dig a bit more into these diseases that I've heard a lot about. I've lived with people who've suffered from them, and I just want to know a little bit more and spread a bit more knowledge about them. So next month, we're going to be talking about invisible diseases. Hope you can join. Thanks for joining tonight. Thanks to anyone who watches this later on. It was cool.